I am Dr. A. Anita, belonging to the Department of Chemistry. In this module, we will discuss about the depression of freezing point. In the previous module, we have seen about the lowering of vapor pressure and the elevation of boiling point, which are some of the colligative properties. In this module, I will discuss about the next colligative property, depression of freezing point. This depression of freezing point comes in our day-to-day life. When you are cooling the water to ice, that when you are freezing water, it will get freeze at 0 degrees centigrade. When you are freezing water, it will get freeze down at 0 degrees centigrade. But if you add a pinch of salt or sugar to it, its freezing point decreases. When you add sodium chloride into it, its freezing point reduces to -4 degrees centigrade. That is called as the ice salt mixture, which has lower temperature than that of the freezing point of the water. Now we see the relationship between the freezing point and the lowering of vapor pressure, and this is the graph between the vapor pressure versus the temperature. When you take this pure solvent, when you reduce the temperature at one particular point, its vapor pressure begins to decrease at a faster rate. That temperature where it begins its lower pressure is called as the freezing point of the solvent. But when you add little amount of solute into it, it forms a solution. When the solution is reduced to its lower temperature, at a temperature lower than this, it begins to reduce its vapor pressure. The temperature at which its vapor pressure gets lowering is called as the freezing point of this solution. When you add some more solute into it, it forms the solution 2. And when you are cooling it or reducing the temperature, at a temperature much lower than this, its vapor pressure begins to decrease suddenly, and that temperature T2 is called as the freezing point of this solution 2. Therefore, when you are adding more and more amount of solute, the freezing point decreases. Hence, the depression of the freezing point, that is the reduction in the freezing point of this solution as well as the solvent, is called as the depression of freezing point, and it is directly proportional to the vapor pressure. That is given as the reduction in the temperature of the freezing point. That is, the freezing point temperature is directly proportional to the lowering of vapor pressure. Now we have to consider this line CD and CE and FD are nearly straight lines, and therefore the triangle BDF and the triangle BEC are similar triangles. When you come to the properties of the similar triangles, DF divided by EC will be equal to BD divided by BE. DF is nothing but the reduction in the freezing point of the solvent and the first solution, whereas EC is nothing but the difference in the freezing point of the solution 2 and the pure solvent, whereas BD is the lowering of vapor pressure between the solvent and the first solution, and BE is the lowering of vapor pressure between the solvent and the second solution. From this, we can come to the conclusion that the depression in the freezing point is directly proportional to the lowering of vapor pressure. From the lowering of vapor pressure, we can come to the conclusion. Here, the vapor pressure of this solvent is taken as a constant value, and therefore the relative depression of freezing point is directly proportional to the Revolt's law, that is P minus Ps divided by P. Therefore, this term is called as the Revolt's law, whereas the P minus Ps divided by B according to Revolt's law is taken as W into capital M divided by capital W into small m. That is, small w is that of the weight of the solute. Capital M is the molecular weight of the solvent, and capital W is the weight of the solvent, and M is the molecular weight of the solute. As the molecular weight of the solvent is taken, if you have taken water, its molecular weight is 80, and which remains constant. We are neglecting the term capital M into it. On neglecting capital M, this equation comes. Here, this term P minus Ps is nothing but the depression of the freezing point, and as it is proportional, we are removing this proportionality by applying a constant that is called as the proportionality constant. That proportionality constant is nothing but a freezing point constant or cryoscopic constant or molar depression constant. When this, how do you find out this value of this depression of freezing point constant? When all other terms are equal to 1, then it will be equal to the depression of the freezing point. That is, this cryoscopic constant is equal to the depression of freezing point when this W by M, that is the number of moles of solute, is equal to 1, when 1 mole of solute is dissolved in 1 kg of the solvent, or else 1 mole of the solute is dissolved in 1000 grams of the solvent, then we can find out the cryoscopic constant. And cryoscopic constant is a constant for a particular solvent. If you are taking water as the solvent, its cryoscopic constant is a definite value, and if you are taking benzene or any other organic solvents, and its cryoscopic constant is a constant value and it does not depend upon other factors. The cryoscopic constant can be found out by some other means, that is called as the latent heat of fusion. This cryoscopic constant can be found out when you are knowing the gas constant and the freezing point of this particular solvent. When it is divided by the latent heat of fusion, we can find out the depression of cryoscopic constant or depression of freezing point constant. From this equation can be useful to find out the molecular weight of the unknown solute. And this is the previous equation, and when you are rearranging this W by 1000, this 1000 in the denominator of the denominator gets into the numerator. Therefore, on rearranging this equation, the M can go to this side and this depression of freezing point can come to this side. Here 1000 is a constant and cryoscopic constant is a constant for a particular solvent, and we are taking this W is nothing but the weight of the solute, and this is the depression of freezing point, and here it comes the capital W, that is nothing but the weight of the solvent we have taken. From this equation we can find out the molecular weight of the unknown solute using this equation, and that is why the colligative property has its important role. Then in this equation, the only unknown parameter is the delta T. How do you find out the delta T? That is the determination of this depression of freezing point, and this can be done by many ways. One such way is the Beckmann's method, and this diagram clearly indicates the pictorial representation or the equipments required for the determination of the freezing point by the Beckmann method. Here it consists of a test tube with the side arms in order to add the solute or solvent into it, and where there are two holes. In one hole we have to attach the stirrer, in the other hole a thermometer, that is the Beckmann thermometer, has to be inserted, and this stirrer can be used with cork in order to avoid its dashing with that of the thermometer. This side arm is used to add the solute into it, and there will be an air jacket, that another glass tube, in order to provide the empty space so that air is allowed to flow into it, so that there can be the direct measurement of the temperature can be taking place. And in this beaker there is a freezing mixture. The freezing mixture is nothing but the combination of the ice as well as the salt in order to freeze this. First of all, we have to take a definite amount of solvent in that of the test tube. We have measured 10 to 15 grams of the solvent into it, and we have to keep that into the air jacket, followed by we have to keep it in the freezing mixture. On keeping it in the freezing mixture, its temperature begins to decrease. At one particular point, its temperature remains the same, remains a constant. That temperature is called as the freezing point of the solvent. Now we have to, at that time we have to stir the solvent so that the latent heat present within the solvent has expelled. Therefore, its temperature remains the same after some time, after expelling all the latent heat, and that temperature is taken as the freezing point of the solvent, and this procedure is repeated 2 to 3 times in order to get the same freezing point. After that, you have to add a little amount of weighed amount of solute into it. Now I am adding solute into this pure solvent. Now it becomes a solution. After that, we have to keep it in the freezing mixture. Its temperature begins to decrease. After one particular point of temperature, it begins to freeze. At that time, its temperature remains constant, and after that you have to stir the solution in order to expel all the latent heat, and then the temperature remains constant. The difference in the temperature between the freezing point of the solvent and the solution alone is measured by the Beckmann thermometer. The difference in the pressure measured by the Beckmann thermometer can be used as such in order to find out the molecular weight of the solvent. This depression of freezing point is usually used to calculate the molecular weight of the unknown solute, and for that we have to use the Beckmann's method in order to find out the depression of freezing point. This depression of freezing point, from that we can find out the molecular weight of the solute. This depression of freezing point has its important application in the industry field. When we want to reduce the temperature or the freezing point of some of the substances, we have to add some solute into it. If we want to reduce the temperature of the freezing point of the substance to a much lower amount, we have to add the solute with higher molecular weight. If the molecular weight of the solute is lower, then there will be a slight reduction in the freezing point depression. If the molecular weight of the solute is larger, then there will be a sudden decrease in the freezing point. That by using the definite amount of solute with the corresponding molecular weight, we can reduce the freezing point of solvent to any extent. That is the industrial application of the freezing point. Whenever you want to go, there is only a limited amount of solvent. If you want to reduce its freezing point, then we can add the solute into it. Thereby we can achieve the depression of freezing point, and that will be acting as a good solution also. And this is the important application of the freezing point. Thank you.